What's up, guys? My name is Michael and welcome to my YouTube channel. Today we are going to upsolve the next problem on AtCoder. The last problem, I think, 174. I think AtCoder last one. I'm pretty tired right now because I'm pretty exhausted. I couldn't fall asleep yesterday, but we are still going to do this. Yeah, I've had issues with sleeping, but whatever. Okay, this is the last problem. Range query. Okay, so whenever you see a range query question, it's probably has to deal with segment trees, right? Because that's like range query. So that's probably most likely what it will be. Let's hold up. Let me just do a pop-up chat. Okay, so you have n colored balls arranged in a row from left to right, and the color of ith ball from the left is Ci. Okay. You're given Q queries. How many different colors do the lth through the rth ball? How many different colors do the ith to the L to the R from left to right have? Okay, so how many different colors? So the color from the left ball is C of I. Okay. So what we could do is we could build a segment tree base and then do that. So let's see. What if we don't use a segment tree? Let's try doing it. Just try doing it. Doing it a very brute force solution. Try to do that first, and then see what we could do there, because that way is probably the most straightforward way, but I don't know. So let's try to use a straightforward way to solve this problem. So I'm really tired now. Holy crap, I'm super tired. Okay, so let's see, CI, so we're gonna read CI C2. Okay, so we're gonna read all the values CI C2. Okay, so let's do this. Let's call our array C. And then we're gonna read all values from up to n. That's what we're gonna do. Okay, and then we're gonna read C of I. Okay, here let's do a CN. That's what we should do. Okay, so now from this point on, yeah. Okay, so we're gonna read Q queries and read in L1 and R1. So let's do like a L and then R. Yeah. Yeah, like that. And then let's do while Q minus minus. We're gonna read in L and R. And then we're gonna do like a solve. Let's create a method called solve. So we do like a solve LR. It passes in LR. Okay, yeah, so we pass in LR. What we could do at this point is to use C. Yeah, okay, so let's create a global variable of C. So it's less, wait, does it even know about n? Yeah, it doesn't know about n. So do C is equal to vector LL. Okay, yeah, all right. So yeah, so by the way, I got a comment saying that I use LL as long. That's okay in competitive programming. It's not okay in like actual problem solving. It's not okay. Hey, how you doing? If someone's in the chat, how you doing? This is the first time I'm actually live streaming at this time, so yeah, it's kind of crazy. I don't actually live stream at this time normally. Let's see. Okay, so if you're new in the chat, we're just solving the last problem, F range set query, and basically you're given the colors of balls from left to right, and you need to calculate how many different colors from the left to the range of left to the right range. The number of different colors they have. So let's see. So first, let's look at this. We have 1, 2, 1, 3. So the range of 1 to 3. How many different colors there are? There's, let's see, range of 1, 3. So 1, 2, 3 have, from the left, have colors 1, 2, and 1. 1, 2, and 3. Okay, so when they say range, they mean by the index. Yeah, they mean by index. Okay, so they don't actually mean like how many different colors are 1, 2, 3. There's 3 different colors. Okay, so they have that. 2 to 4. So the range from 2 to 4 is 2, 1, 3. So there should be 3 of that. So yeah, that's the answer. 3 to 3. There's only one range. 1. Okay. So yeah, I think you have to build a segment tree actually. But let's try to brute force it. So one way to brute force it, you would just loop from L to R and just count how many different you just do like a count. It's how many different values there are. So from L to R, just count if the ones are not equal. So what you could do is you could actually insert into a set actually. So we could do like a set count, yeah, count, and then we do a count dot insert C of x, yeah, C of x, and then after that we could do like just return, or we could do C out count dot size. Alright, so what we're doing is we're inserting each value into a set, so it removes all the duplicates, and then that'll give us the number of different values. Yeah, so we could do that. Let's look at this, LR. I'm actually do n plus 1. So I'm indexing from 1 actually. Yeah, so that'll actually make the L and R actual right indexes, because they're indexing from 1. Okay, so once we have that, yeah, that's all we have to do. Pretty much that's all we have to do. Do that for that many number of times. But there's an issue with this. It's not efficient actually. So let's see. Let's see if this code works for now. My screen's stuck. Oh. Sorry guys, why is my screen stuck? Huh. They're not receiving enough video for smooth streaming. That's weird. Is it still stuck, guys? Still stuck? Hold up. I want to see if is it still stuck? Now it is visible. Okay, so now it's visible. Okay, thanks. I don't know why it was stuck for a second, but let's go back here and try to. Okay, so based on what we see, 2, 3, 1. Yeah, so this actually does work. This code actually does work. But it's not efficient, I think. So we could use a segment tree for a range query. 1, 2, 2, 1, 2, 2. I think this is right. So let's try submitting it, see if it works first, and then we'll see if we could use a segment tree. So if we get TLE, we probably can't use a segment tree. Maybe we won't. Oh no, we got TLE. Damn, that's annoying. Okay, so we're gonna have to use a segment tree. Can you guys still see my thing? Okay, it's visible. Okay. So it just lagged for a minute. Okay, that's good. So yeah, now so we got TLE. So what we need to do is we actually need to create a range query create a segment tree. So a segment tree helps you do range between ranges. So I actually don't know how to implement it by myself. So I'm gonna use Geeks for Geeks. Hacks. I know hacks. Okay. So let's see. So Geeks for Geeks. I don't think we need update value. Okay, it might be is there a better way to do segment tree for this one? I'm getting like weird updates. Let's see. XOR of a given range. Let's see this one. Okay, so yeah. I think it's about the same thing. So let's just go back to the first one and do that. Okay, so segment trees helps you do like ranges. So what we could do is let's just use this code. So first we're gonna do like a construct segment tree. We could do that. So we'll do it like this. Take this code, put it right here. So this would construct a segment tree. So let's, instead of array, let's do a vector. Vector. Long. Let's do vector long. Let's do L long. This is gonna construct a segment tree util, and then we're gonna return the segment tree. So let's see. What do we have to change for this? The height. Let's see our values. Do we need long? Sometimes we don't need long. I feel like we don't actually need long. Oh wait, 5 times 10 to the 5th. Is 10 to the 5th the range? Alright, whatever. Let's just use long then for all these. So we're gonna use long for everything. This makes the height. So the height is like log base 2 of n. N is the number size. Maximum size 2 to the n plus 1. Yeah. Whoa. Okay. This is actually not good practice. You shouldn't do this. That's actually really not good practice. I don't think it's a good idea to create pointers like this. It would make more sense if you use like 2D vectors instead of actually using pointers like this. Let me see if there's like an actual segment tree implementation. 2D vectors, C++. Because like it's not a good idea to do. Yeah, okay, so we got it. We got one right here. It's not a good idea to do a bunch of pointers. I don't think it's a good idea to do a bunch of pointers because you don't know what because you generally, if you use a bunch of pointers, you might screw something up. So yeah. Yeah, so let's use this. So this one, you build a matrix based on this. Is it based on 1s and 0s? Store 2D. Okay, let's use a class then. We're gonna use a class. So let's do something like this. So remember, we have to do this. Yeah. Okay. Well, we'll use this. So let's do segment tree. So we're gonna create a class called segment tree, which is like what we're gonna implement. Let's just type this out. We could learn it along the way. Segment tree 2D. Let's see. So this is just like a class that has like all the methods and stuff. So these are instance variables, segment tree, vector, vector, segment tree. Okay, so let's do that. Vector, vector, segment tree, st. So that's 2D segment tree. Then we need a matrix. So vector, vector, int, matrix. Okay. Now what do we need? Okay, so we have m and n. So let's do that. I think that's just the size. Okay, so now we're gonna actually do the building, the whole segment tree. So first thing we need to do is we need our instance variable of the matrix that we're building. So we'll do that. Public segment. So we need a constructor. Vector, vector, int, matrix. Mat dot. Let's do mat. Yeah, let's call this mat. Mat is going to equal to matrix. Okay. Why can't I do that? Why can't I actually not do that? Why can't I do that? Matrix. Vector matrix. Mat is equal to matrix. Why can't I do that? Vector, vector, mat. Vector, vector, mat. Vector, vector, int. Matrix. Maybe they require, what do they require? No operator O equals O equal. Crab. You can't store equals equals. Do you have to overwrite equals? Okay, there might be another implementation. Segment tree, C++, vector, STL. Oh, okay, we could use this one. Oh yeah, okay, but let's use this one. Okay, yeah, it's actually a good idea. This is a way better idea. So we have the array size, we're gonna multiply it by 2, and then we build our tree like this way. So let's do that. So let's actually not use this. Maybe it's better for, maybe in the future we'll create a class. I don't know, for now let's not do that. Okay, so let's create our tree. So yeah, sorry guys, I'm not gonna use this. In the future we'll build a segment tree. Maybe we'll look at like other people's code and see what they did. Okay, so we need the size of the tree. So yeah, to build the size of the tree, let's do a vector tree. It should be 2 times the size of the array. So tree okay, so we'll do a void build tree vector array. Let's do that. Array. Whoops. Let's see. Vector array. So now we're gonna go through every. This is just setting the leaves. So it's just like setting the bottom part of the tree. This is r dot size. Actually, we're just using C. We're building it off of C, so we don't actually need this. C dot size. So yeah, here we're actually going to go up to n, so like size -1, starting from 1, because we're indexing from 1. So then we're gonna do like tree at let's see. Damn, if we're indexing at 1, this might complicate a bit things. Whatever. Okay, so for the 0, we're gonna have a placeholder I plus n, n is going to be the size of our array, so that's actually size c dot size, I think. C dot size. Let's do that. Let's call this n is going to equal to c dot size. Yeah. Okay. So then now we're going to do n minus 1. Okay. So c plus 1 is going to equal to c at I. Yeah. Okay. So that works. Now we're going to do, so that builds the leaves. Then we have to do the querying. So this is going to calculate its parent. I think this is going to add the sum. So we actually have to change this later on, however, when we build our tree. So this is calculating the sum for each range. So yeah, we have to change that. But for now, let's just leave it as is, because that's what yeah, that's what we should do. I to n minus 1. This one is gonna be size minus 1. N is size minus 1. This is gonna be n minus 2 actually. Tree at I is gonna equal to tree at I. Yeah, so this is getting the different ranges. So this is divided by 2, and this is divided by 2 or 1. Okay. We're still gonna do that. So we'll do this. Okay, so this is like getting the ranges. Do we need to update a tree node? I feel like we don't have to, because like we're not really changing the tree, right? We're just getting the different queries. So yeah, yeah, we don't actually need that. This is define the sum in the range. So let's see. Let's just have it in case. All right, I'll copy this. I don't think we need to update the. I actually don't think we need this update tree node. Okay, so what we need is to query the tree, and we need to build the tree. Okay, so building the tree might be a little harder. Querying the tree, we don't need to add so. Excuse me. So if we're querying the tree, okay, let's think about this for a second. N is just c dot size. Okay, so this range query is just getting each of the different ranges and adding it up, setting it. So here we need to change this so that we're actually getting each of the different numbers of colors, the different colors, right? We need to calculate the number of different colors. So this one originally these just sum up the sum. We actually need to calculate the number of different colors for each of them. So we need to do that, and this, I think the sum we could actually leave it. We might actually could leave this, because if we get the different ranges in each value, we don't need to summing it up is just for each range is fine. This is fine. Okay, we don't need to, this function is not even needed, the whole update node, because we're not changing the node, right? Okay, so we need this, we still need this. I think this is fine, querying it, because we're just adding. This is the different part. So we need to find the number of different, for each leaf, right? We have a color, we need, for each color, we need to find the number of different, what's the word? Different colors, right? So for each range. So we can't just add up the, can't just add up all the leaves for the given range. So we need to figure out this, so this part is, we need to figure it out. Okay, so I think we could do something the same, similar as solve. So we could use like a set, I think, and then insert it and then find the size. So we might be able to do that here. Oh, not this one, this one. So let's see. Okay, so once we build all the leaves of the segment tree, let's find each of the leaf. So okay, so here the tree has all the leaves as each individual color, right? We need to calculate for each leaf the number of different colors for each leaf, so then we could sum them up. So yeah, that's the hard part. Let me think. We might be able to do this actually. Let's see. Wait, I'm not sure what this is actually doing. Is this the second leaf? This is the I divide by 2 or by 1. Wait, what is this doing? I don't know. Save I XOR 1 in a variable and to not compute the same operation twice. I XOR the, I don't know which one you're talking about. This one? This one. So, hold up. Okay, so I shift left is multiplying by 2, I think. Or is it dividing by 2? Let's see that. Shifting left by 1. Yeah, so that's the same as shift. So I think this is just 2 times I. And this is just 2 times I plus 1, I think. Well, what happens if you OR by 1? I'm pretty sure the other one is just, wait, let's see, shifting, I think this is just 2I plus 1, or 2I minus 1. Hold up, let's see something. What does I shift left or by 1 do? Hold up, okay, I'm gonna do like a quick test real quick, because I don't know what that does. So let's take a number, let's do like 3, and let's see out X shift left 1. Let's do like a y is equal to X shift left by 1 and then OR by 1. I think it's just 2x plus 1 or 2x minus 1. I don't know though. Let's just run this. I'm not sure. I don't know what this is doing. Oh, it's okay, so it's 7. So it's 2x plus 1. Yeah, so that's what it is doing. Okay, so yeah, okay. So here this is actually just 2I plus 1. 2 times I plus 1. Okay. Let's just okay, so that's each of the leaf. We don't need update node. If we don't need update node, I'm just gonna delete it actually, because we're not updating each node. Okay, so now here's the problem. Here's the difficult part. How are you gonna get for each node, we need to find out the number of different colors for each between two leaves. So that's what this tree of I has to be. So like, right, so we need to, I'm thinking we could just take tree at 2 times, the left leaf and then the right leaf. And then maybe we could put them into a set. And then add, technically you don't need a set. You could just check if it's left or right. But yeah, okay. Here's the difficult part. If you take each of the leaf, so let's say I have like 1, 2. If I'm building the segment tree based on the leaf, so like let's say I have 1, 2, 1, 3, right? So that's the leaves. So between leaf 1 and 2, that should be 2. 2 should be the number of different values, and then between 1 and 3 it should be 2 also, because that's the number of different colors. And then from 1 and 1 it should be 0. So you would have to do, I'm trying to think how are we going to build this. Yeah, so basically I'm building a segment tree based on the current input, because we're doing range queries, right? That's what we're doing. So yeah, so if we could do, let's see, because we want to build a segment tree for each of finding the different number of colors, right? So for each leaf, we should find the different number of colors, I think. So each of the leaf stores a number for now. Now we need to do the, let's see. I gotta draw this out. I don't know what I'm gonna install software so I could actually write on top of the computer, because like you guys don't know what I'm writing out. So let's label a segment tree as leaves of 1, 2, and 1, 3. So like 1, 2, 1, 3. Okay, and then we're gonna have 1, 2. The number of different colors is going to be 2, so that's that. 1, 3. The number of different colors is 2, so that's that. Whoops, sorry guys, my alarm just rang. Okay, so let's see. Let's go back to our segment tree here. Let's see. Let's look at how they did theirs. Yeah, so these are the like range queries. Let's see. So we have, for them they have numbers. Let's see, what numbers do they have? 0, 17. Wait. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so 16, 17, 0, 1. Oh, 16, 17 is the index. 0, 1, sum is 0, 2. Wait a minute. Oh my gosh. Let's see, 4, 6. I'm not so sure how this. So they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Shouldn't their leaves be that? 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, yeah. Let's see, for 12 to 13, their sum is for 12 to 14. Why is there sum 14? Wait a minute. Yeah, I don't. Yeah, I'm not gonna use a linked list. Yeah, we can't really access the values in a linked list. Let's see. That's the main reason why I didn't want to use those pointers in the other implementation. Okay, so back to this. Let's try to do. What if I just do? So what if I create a set and then I add the ones that are distinct? So I could do like set distinct. And I'm gonna insert the values d of tree of I, 2i, and then insert distinct tree of 2i plus 1, and then here we just find it's just distinct dot size. I don't know if this would work, but let's comment this out. So I'm not so sure yet what I'm doing. I don't know what I'm doing actually, guys. Because we want the number of distinct elements, right, for each of the leaf. That's my idea how this is going to work, but I could be completely wrong. For solve, we're just going to pass in query LR. See out query LR. Alright, let's try this. Oh, we gotta build the segment tree first. So I gotta call build tree. So yeah, I gotta do that. Alright, let's see what this gives us. So let's pass in 1, 2, 1, 3. Alright, let's go in here. Let's see if we don't have. Oh damn, we got it out of bounds. Oh okay, I didn't set the size of the tree. Tree has to be 2 times of n. So let's do tree is equal to vector let's see. Do we use long for that one? So let's use long for all of the query. No. Oh yeah, that's right. Yeah, that's it. Okay. Tree is gonna equal 2 times size. So tree is gonna equal to long of 2 times n. Let's add 1 because yeah, we're indexing from 1. Okay. Let's do this. Alright, this is just setting the leaves. Whoops, what happened? Subject ran out of range. What just happened? It's 2 times n plus 1 though. Oh, maybe we have to do 2 times n plus 2. You don't know how strange like these trees work, because there's when you start indexing from 1, it starts changing everything. Okay, so let's see. We have 1 to 5. So let's do 6. How big is a tree? Tree is 10. So let's see. We have 1, 2 plus 5, 3, 4. Yeah, okay. Alright, so we got that. Alright, so now we have to build the ranges. I don't know if this is actually right. Let's see, a tree is... Oh, what just happened? Why is tree not... tree should be, yeah, okay, so 6, 7, 8, 9, 10, 6, 7, 8, 9, so 1, 2, 3, 4, 5, 6 is the right values. Let's see the range from 1 to, let's see, what did that change? First range to 3, from 3 to 6. Hold up. Did that change anything? So 1, 2, 1, 3. Okay. Well, let's just see a range. What is the first query? What did it give us? What did the first query give us? It gave us 2. Okay, I think that's right. That is right. What did the next query give us? 3. Let's see, 2 to 4. That is right. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, that is right. Let's look at the next query. It should give us 0. Oh no, it should give us 1. Whoops. No, what just happened? Give us 1. Gave us 0. So from the same number, it can't be. If we're querying from the same number, we should give 1. So that's we have to change that. Okay, let's go back up here. Let's see. Plus equal LL plus equal. This is right. I think something was wrong with our distinct. I don't know. Let's see. Sure thing. Let's see. Sure thing. I should create like another algorithm series actually. That last one wasn't that good, but I'm going to try. I'll create like a segment tree tutorial or something. I don't know. I should do that. I should create a segment tree tutorial. Or maybe start with like suffix array. I don't know. Okay. Back to this. 2, 3, and 1. Color is just one color. So yeah, I'm having an issue with this last color one. Let's see. Maybe we could do something like -1. Try this. Will that fix it? I'm just giving random options right now. Maybe it'll give me out of bounds. Who knows? No, it still gives 0. No, that's also wrong. That's actually wrong. That is actually wrong. Okay. Let's see. 3 to 3 should give us. Oh, including R. Try that. We try that. Nope. 4, 3, 4. 1, 3, 6. No, that's not right. Okay. That shouldn't be including R. Yeah, we don't need this anymore. Let's get that out of the way. So this, we're just trying to get the distinct numbers. Let's see. Let's see what happens when we do 3, 3. Why it's giving us the wrong answers. So let's see after it does all this. Two, 4. Okay, 3, 3. It should give 3, 3. Okay, so let's see. What did it just do? 8. Result 0. What did it do? +1. Maybe we have to do that. Or this n minus 1. Oh, wait. Oh, I got it. Okay. If L is equal to R, we just return 1. Okay. That would make more sense, yeah. So then it's yeah, okay. So I think that's right. Let's look at the other test cases. Okay, it should give us 1, 2, 2, 1, 2, 2, 6, 3, 3, 3. That's what it should give us. Okay, so we got 1. Ah, damn. We got 11. Why did we get 11? 2, 4. Should give us 2. Okay. Let's see. We got something wrong. 1. We have 1. We have 1. 11. We have 11 for some reason. 5, 6. 2 to 4. 1, 2, 3, 4. It shouldn't be 11. It should be 3. It should be 2. It should be 2. Number of distinct numbers. Yeah. That's not right. That's not right. Let's see. All right, thanks. Thank you so much. Yeah, I'll create a different tutorial for algorithms. A completely different one. Okay. Back to this problem. 2i plus 1. What is a problem right now? What is our issue here? What is our issue? 2, 4. Okay, let's look at this. Okay, we should actually do a build from here. Okay, so building the leaves is fine. Still taking a while to build the leaves. Okay, so let's see, from here, from the range of 2 to, let's see, so from 2 to 4, it should give us so from range of 1, let's see, tree at original 1 should be 2. Yeah. Okay, yeah, that's right. Next one. Why is distinct 4? Oh. Oh, okay. Oh. I think I know why. Distinct should be here. Okay. Whoa. That's not right. Oh, whoops. Still 11. Why is it 11? How long have I been live streaming? I feel like it's been an hour. Okay, it's been an hour, I think. It's been an hour. So what we're actually going to do, we should actually just look at one of people's solutions, because I don't feel like talking way too long. And I think our solution is sort of correct. You definitely have to use a segment tree or a Fenwick tree. All right, so yeah, he used one of these. What? That's not a segment. I don't think this is a segment tree. Is this a segment tree? Left, right. Maybe it is. The bit of one. I don't know. Let's go back. Let's look at this. I don't know what I'm doing. Don't know what I'm doing. You can take the bit. And place one. Is this a Fenwick? Okay, wait. Fenwick tree. Let's see something. Let's see, Fenwick tree, binary index tree. Yeah, I think this is what they're doing. They're using a binary index tree. Let's see if there's like a segment tree one. I don't know what they're doing at this point. I don't know what they're doing here. That's not... I have no idea what they're doing at that point. I don't know what that guy's doing. Let's see. Alright, let's just open a bunch of solutions. I don't know what he's doing. Is this a segment tree? No, this is a bit tree. Why is no one using a segment tree? Let's look at this. Okay, if everyone's using this, then let's just use it then, I guess. Because I'm not so sure how else we would. I'll give like an explanation about how to do these problems. Maybe we should just do what they do. Bit. And by a negative I. What does that do? Huh. I don't get it. Let's look at some other solutions. I think this is, yeah, okay, I think this is a segment tree. No, it's a bit tree. All right, if we're gonna do this their way, I guess we'll just do it their way. Because I feel like everyone's using a bit tree, so, which I'm not sure what a bit tree is. I'll give an explanation later. Because on Geeks for Geeks it says it's like sum of powers of 2. Binary index tree, bit tree. Each node stores the sum of the elements of input array. Initialize all the values to 0. What is the difference between this? Less space and is easier to implement. Each node is the sum of the elements of the input array. Go to the parent of the index to remove the last bit of the index. So then you do that. Return the sum. Alright guys, I'll give a tutorial of this after I want to understand this. But for now, let's just see let's just do what they do. Okay? Okay. Yeah, let's just use a bit tree then. I don't understand what a bit tree is exactly, but I think it's fine for now. Okay, okay, so they use a max size of 5 to the 7th. Let's do that. Max size 5 to the 7th. So we don't have to do like inputs. Then they do like a struct node. LR left, right, and then the input. Actually, they don't even do that. They don't even use it. Okay then. Tree, NM, visited. They have a visited array? Okay, low bit, they return the current value and by the negative. I don't understand. Here they loop from x to n and then add up all the low bits. I don't understand actually. Add up all the low bits. Okay, if it works, no complaining. Let's add up all the low bits. Then they subtract each bit. Okay, subtract every small bit. Okay, I don't know how that helps you though. They have a comparator. Oh, that's fun. That's funny. Use a comparator. I think the comparator is just comparing left and right. Left with right, yeah. Okay, so then they have like a node, a class of node, which is left and right, and then the current value. Why do they call it QN? I don't know why they do that. Okay, so what do they do here? Read all the values of AI, then scan F to Q, L and R. Huh, that's insane. Oh no. Oh, wait. Oh, okay, I get what they're doing. I get what they're doing. Okay, I know what they're doing. Okay. So once they read this, N and Q, because because they have the final value of n. Let's call this little n, little q. This is just seeing in the values. So this is just reading in the values. So let's do that. And that's going to read in a of I. Yeah, so that's reading in the values. Then when they read in every query, so they're going to go through all the queries. Let's just do while q minus minus. And then they're going to read in query big Q? Oh, little q. Little q of, oh wait, let's see. Okay, so they have like each node, they read in each node. Let's call this M. Okay, let's do M. Then they read in every query. Okay, so they read in every query for the left and the right and the current index. Okay, so that's a really smart. That is actually really smart. For every query, they read in the current query dot L, and then the right query, and then yeah, dot R Q at I is equal dot I is equal to I. Why is this not working? Must have pointer to object type. Is that what they mean? Let's just do like left right. So let's do CN left right. And then let's do like this. Left is equal to Q.L is going to equal to left. And then we do the same thing here. I still can't do it. What if I do this? No, I can't do it. Star? Why can't I do it? You're forcing us to use scanf. Alright, let's just use scanf then. Okay. It's like deprecated. Then we're gonna do pointer dot L pointer dot R. Huh? What? How is their code even running? That's actually kind of crazy. That doesn't make any sense. Wait, let's look at another one. Let's not look at this one. Let's look at this one. There's another code. They used to. This one. Yeah, this one. RJ at RW. Okay, yeah. Let's use this one. CN RJ of I. What's RJ? RJ is a struct. Okay, yeah, so it's a struct of left, right, and then the bit. Okay. So they create like a struct of node. Oh yeah, so let's do that. Let's call this struct node. We're gonna do this. So we're gonna do this one. We're gonna call this it's called node. Node tree. Tree. Yeah, tree 5,000. Last bit's 5,000. Let's use this guy's code. Yeah. Okay. Let's do tree. So we have bit. Last bit. Let's do that. Okay, let's use this. So yeah, we're not going to do this. We're going to use this. We'll call this node. Let's call this tree. Yeah. So now we have those. We still need lower bit. Update query. Yeah, we just need update and query. So let's do update. Let's take this code. So they're adding the lower bits of each of them. I'm not sure what they're doing actually. I literally don't know what they're doing. Are they adding the lower bits or? Okay, I'm gonna give a tutorial on how this works later on. I'll read it. But for now, let's just do this. Yeah, then read in the values right here. Q. A vector A. Let's see, vector. Okay, then K. Read in those values. Let's do the Q. Read in, this time we're going to actually read in node at tree at, what did they do? Tree at I dot left, tree at I dot right. Okay, what is the problem? Let's have class type. What is the problem? Node tree. Is that what they did? No, it's definitely just tree. Tree at I dot L, tree at I dot R. Pretty sure that's right. Oh, I redefine these. My fault. Yeah, okay. Then we said tree at I is going to equal to, ID is going to equal to I. Okay. Let's do 0. We're indexing from 0 now. So let's do this. And actually, we're not, since we made it all 5 million, I don't think it matters. Yeah, we made A equal 5 million. Actually, I don't know. It is what it is. Let's do the 0 and then Q. Yeah, easy. Easy peasy lemon squeezy. Okay, sort the edges. Sort tree with tree plus K. Whoa. Whoa. Okay. Tree plus K, which is our Q. Huh. Okay, so sort that. Start at the beginning. Update each edge with a -1. Go through the beginning. If the last bit is not -1, we update it to -1. Set the last bit equal to I, update it. While it's less than k, add by 1. Query it, subtract the query, add 1. Print the answer. I have no idea what they're doing at this point. But it sounds legit. Answer, how did I put answer? Answer should be 5 million, right? Oh, answer is k. Okay. Let's do vector answer is equal to q. Yeah. Okay. Yeah. After that, just print out every single answer for k. LC, what's LC? LC. Oh, that's a new line. Huh. Okay, I have no idea how this works, but I don't know how this works, guys. I don't know how this binary tree works, but yeah. Fee set. I'll look at it. I'll look at algorithms live, how fee set works. I don't really know how it works though. I'll look at it. Let's just see. What's CE? I've actually never had this error before. Oh, compiler error. Huh? Oh, whoops. What is the problem? I'm not sure what I did wrong. Alright guys, I have to end the live stream now. It's been an hour. Sorry guys, I couldn't figure this problem out. It's pretty difficult. I hope you guys enjoy this video. Rate, comment, subscribe. I'll check you guys later.